So I want to, let's see, I think I'll just start with the homework today, because it seems to be, there's a lot to it. And it ties in with what the rest of the chapter notes are too. So, let's see. So we got, this paper is about, so it's 2023, kind of recent, but basically they make alloys of these transition metals, except aluminum's not transition metal, but everything else is a transition metal. So it means that they can have different bonding states, like they can bond 4 or 5 different valence states, right? So they can have different oxides. Anyway, and then also these metals all have about the same size. Like, let's say I wrote down some here. They're all about like 1.26 angstrom for like if you make a metal and get the D spacing kind of thing. These are the right notes. These are just a lot of notes. Anyway, so they fit into a crystal. They just make a simple BCC crystal. So if you look at the diffraction, so the diffraction is really simple. It's got 3 peaks, like 110. So these are the Miller indices for the reflections. Oh, sorry. Yeah. Sorry about that. Let's see. Let's see. Good. Yeah. All right. So they're making these alloys from this. It's a mixture of transition metals. So, I mean, the transition metals can have different oxidation states. They have different number of bonds. Like titanium has usually got 4 bonds, like carbon or silicon, but basically it can have like 5. So it can switch. So they're used for catalysts because of that. So that extra bonding orbital can kind of hook onto an organic molecule in a chemical reaction. So anyway, these are almost all transition metals, and are all, like, if you look at their atomic sizes, they're almost exactly the same size. So they can swap kind of the sites in a BCC lattice, which is like simple cubic, but it's got an atom in the middle, right? So anyway, it's a pretty simple crystal lattice. Like, it's the crystal, even though it's a complex mixture of things, like the diffraction from it's just got 3 peaks in it, basically. It's got a 100 that's weak, and it's got these other 3 peaks. Right, and they basically, no matter what the mixture of the alloy, you get the same position. So the lattice spacing of the crystal remains the same. So it's called they're called high entropy metals because you can take different conformational states. So again, like the entropy is going to be so we got like the entropy. The Boltzmann law says that the entropy is going to be R ln of like the number of states, say, right? Or right. So basically here you can have like Fe or Cr in a given lattice position. So you have kind of like the body-centered atom and then these other ones, right? So body-centered cubic, we can swap all these 5 different metals for the sites, except for aluminum, which is larger. Aluminum's like, all these are like 1.26 angstrom diameter. And then aluminum's like 2.4, I think. So Al is part of it too, but all the other metals can just swap within the lattice. And there's a lot of them. So basically a lot of entropy, meaning a lot of different states. Log of that gives you the entropy, say high entropy alloys because of that. Right. So these things have certain like properties that are better than other alloys. Like they're stronger. They resist corrosion. What else? There's advantages to these high entropy alloys. Not sure I don't think I have the right notes here. Maybe, there are too many papers in here. Oh, yeah. So I did write out notes. Didn't have them. That's not it. All right, this must be it. Not readable. Anyway, so that's basically what kind of what the alloys are. So what they're doing with it, they want to make so they want to make what's called a magnetocaloric material, meaning that you can take it through the so it's a ferromagnet to a so it's going to have a ferromagnetic to a paramagnetic transition. It's like 34 of these slides. Let me get here. Let's see, those don't go to 34. This is what I said. Where's the other one? This one. It's 24. But we did the ferro in this business. So you have the paramagnetic and ferromagnetic states, right? Like here. So ferromagnetics, when it's magnetic and you heat it up above the Curie temperature, it goes to paramagnetic. So it turns out there's some materials that have like super paramagnetic. In other words, somehow they're really so you can think like there's an entropy change here. You're going from ordered to disordered. So entropy is going to be related to the ordering of it. So basically, if you in the ordered state is ordered, so the disordered state is what governs the delta S that goes with this. And they're using that delta S, like T delta S would be a change in energy, and that's going to be the energy of transition that it's going to be using to cool a refrigerator. So it's going to use this Curie transition to cause like cooling in a refrigerator. That's the idea of this whole thing. Right. So this idea is like this could be theoretically more efficient than a vapor cycle for like evaporating a chlorofluorocarbon refrigerant. No, and it turns out, well, you'll find out when you look at the numbers they show that that's not exactly true, but that's the claim they have that this is going to be like a super refrigerator, be more efficient. It's a solid state refrigerator. You don't have to have pumps. So anyway, that's the idea of what they're doing. So they want to study this magnetic transition. So they do a bunch of different things. So they have these things that they talk about: high relative cooling power, RCP, and refrigerant capacity, RC, then magnetocaloric effect, MCE. So there's a lot of acronyms here. Magnetic phase transition, MPT. So I use those throughout the paper. Anyway, so there's the standard material to do this with is this this rare earth metal, which is it's B something, which I had written down. I did my notes on it. Oh, there's probably on the other side. That's why I'm double using paper. Yeah, they are right here. Okay, so the thing that they usually use is GD, gadolinium, which is a rare earth metal, like you never heard of it, right? So basically it's got the highest of this transitions. It's the most paramagnetic of any material. When it gets to the paramagnetic state, it's in the most that you can get of the randomization of the magnetization. And then when it's magnetized, they're all the same, like they're all aligned, right? So it's a magnet. Right, and gadolinium does that at right about a room temperature, which is useful because you want to run a refrigerator at room temperature. So that's kind of like the most useful temperature. So it's the 64 atomic number. So that's the standard that they're comparing this business to. And they've come up with this, not them, but other people have come up. So there's like a couple reviews, like this review by this law person. It's a review of basically this kind of alloy, like a high entropy alloy to be used for this thermoelectric cooling. And she shows similar stuff, but it's not a research article. It's just a survey article, right? So she's got some of the same equations in here, right? So anyway, so what they do is they make this stuff. So they just take all these elements and they mix it together and they put it into an arc furnace and they melt it 2 or 3 times. They make sure that it's mixed. By making sure it's mixed, they do an elemental analysis in the SEM. It's a 10 micron resolution. That's a picture, it doesn't show anything. And they can image just the aluminum, just the magnesium. These are the components that they have. And it basically it's uniform. I mean, there's little dots, but basically it's not kind of domains of those things. So saying they have a uniform alloy. And also they can get this diffraction that shows that the crystal structure stays the same as they add the different elements because they have the same size, so it doesn't distort the crystal. Right, so that means it has a high entropy because the location of an iron versus a chromium, you don't know where it's going to be within the lattice. Or it's a perfect lattice, a BCC, but what's at the lattice site is random, right? And because of that randomness, you get entropy. So it's a high entropy alloy. So it's perfectly crystalline. It's not what you'd think of as a random material, but the randomness is in the positioning of the atoms, which are randomly distributed in the crystal. And they show that that's true by doing this density functional theory simulation, this VASP thing. We'll talk briefly about later on, because the last section here I'll talk about simulations. So we'll talk a little bit about these DFT simulations. Basically, it's simulating the quantum mechanical wave function for the electrons and the atoms, and they can get the potential energy or the free energy of the crystal from that. And then they can figure out kind of how the atoms are distributed in this, and basically they can calculate the entropy and the thermodynamics of the system from that. Right. And they can tell what kind of crystal structure is forming, things like that. So basically they're doing some simulations. So they have a simulation package that they use. So these are expensive to buy. So they bought it, so they use it in this paper, but it's not really the main crux of the paper, but they do mention it. So we'll talk about that stuff later on. And then density of states is something you get from the density functional theory. That's the density of the, here they're talking about the density of the electronic states of the atoms in the system, which gives rise to things like the heat capacity and basically the entropy too, because the heat capacity is ds by t. So basically, this stuff you won't know anything about, but we'll study this later on. Like we'll talk about the density of states when we talk about heat capacity. Right, so that's the basis for understanding heat capacity. So it's kind of like how if you put energy into a material, it's going to get atomic vibrations. Those are going to be distributed over a bunch of frequencies. Like if you have a guitar and you whack it with a hammer, you have 6 tones you get from it. So the energy of the hammer is going into the 6 strings. So a piece of metal also has like 15 different vibrations it's going to do. And that if you look at the spectrum of the population of the vibrations versus the frequency, you'll get spikes. And that's the density of states. Like it's telling you where the energy is distributed in the material. Since heat capacity is how it stores energy, it's storing it by the vibration of the atoms. That's telling you exactly what is causing the heat capacity of the material. Right. So there's a reason you want to know this density of states. He shows plots of that in here. This is incidental. It's not really what I'm asked. Like these are the plots of the density of states versus energy. So energy is h nu, so that's the frequency of vibration versus where the energy is. Like when you whack it, where does the energy go? So it goes into these different states. We'll talk about these plots later on. Right? There's different kinds of vibrations. Like so, basically, we'll talk about those later on. But so there's stuff here. It's like kind of foreshadowing. So when you see things you understand, you can Google and say like, what's density states, what's VASP, but that's not really the crux of what he's getting into here. What they want to get is this idea that as you heat it up, then you go through this Curie transition from ferromagnetic to paramagnetic, and so it turns out so the temperature of the transition is kind of proportional to the energy of the transition. Energy is what they want to get to cool. So they want this to be a big energy of transition. Turns out the temperature transition is proportional to the energy of transition. The Curie temperature is proportional to the energy of transition if it's a ferromagnetic to paramagnetic transition. And this energy is what they want to run the refrigerator, right? So, and then as they add in, so all they do, they take this alloy, so they fix the number of magnesium, aluminum, cobalt, and they vary the number of iron and chromium from 2323 to like 22, 20, 24, and then 21, 25, and 20, 26. So they're gonna have like four of these alloys with different amount of iron and chromium in it. And that's what leads to the shift. So with that, the more iron they put in, the Curie temperature, the energy goes higher and the Curie temperature shifts. So you want it tuned because the original one is at 275 and you want it to be 300. Like, so the yellow one's about in the perfect place, like that would be room temperature. So the yellow one's like in the perfect place. So they can dope it with different amounts of iron to tune the thing to be where they want. And then the other thing they get is so the amount of magnetization versus the magnetic field you put on it, they want that to be, in other words, they want the magnet to peg out with a small amount, because the magnetic field you're putting on is the energy you kind of put in to make the thing work. So if they can get that to be to magnetize quickly, that's good. And these materials have that feature. Like the minute you put any magnetic field on it, zoom, it's magnetized and it's pretty flat. Right. So that's a good feature. So again, so the magnetization thing is coming from this so this is the crux of this Landau, whatever we're talking about, right? In other words, this Landau theory for magnetization. So basically we had this idea, like you're going to write the free energy is an expansion of like even powers of this order parameter. So it turns out his order parameter is m, so it's m squared is what he's looking at, right? So his magnetization, his gamma is m, the magnetization, it's m squared, m to the 4, and he has this a and b. If it's a second order transition, b is positive. That means if you plot, here. That means if you plot m squared versus a magnetic field divided by m, you get a straight line that has a positive slope. And if it's a negative, if it's a second order transition, then this b parameter is negative. It's like wherever, if it's a first order transition, the b parameter is negative, like we had here. Yeah.
So we're going to get a slide.
Oh, you can get that slide in the, if you go to here, right, and then you go to single component systems, like you can get the PowerPoint here, and this is if you do this one, that's a PDF of it. It's easier to view here, and it's like 34, I think, if I remember right. Like this one. Oh no, it's before that's 32 or something. It's somewhere in here. Second order, first order, second order. Right. So it's just a Taylor series expansion, but he takes only the even orders of power because it's symmetric about the magnetization. Doesn't matter if the magnetization is up or down. It can be totally magnetized that way, or that way it's still order parameter 1. Right. So because of that, that has a direction, it's an arrow. So it has to be squared to remove the direction. So you just get 1 and 0 for the other one, if it's perfectly disordered, which would be the case for this gadolinium, right? So it's complicated, but basically, anyway, so it's good for you to weasel through this stuff and figure out what's going on, you know? Anyway, so here the B is positive, it's second order, like a glass transition. There's no change in volume. Right? And then if that B is negative, then it's first order. Right. So that's because it's squared, so you're only looking at even power, you end up with m squared as a parameter. If you look at this, so they've come up with this RO plot, which is a plot of versus m squared. So let's see. M squared is a y-axis, and the magnetization is the x by it's the magnetic field divided by m for the x-axis, because it comes from this. It comes from this equation, which is exactly the same as the equation for the Landau's equation. I know as we have the A parameter, the B parameter, this parameter isn't in the one I showed you. This is like the background part. Then the A parameter is this thing, which is temperature dependent with a T minus TC over TC that I went through last time. So that becomes like a term called eta here. So that's the reduced temperature. It's like the temperature only matters relative to the Curie temperature. Then the temperature is plus or minus about the transition temperature. They don't want to have units, so you divide by the Curie temperature. So it's like the relative index distance from the Curie temperature. That becomes your relative, that becomes a temperature parameter for everything in thermodynamics, becomes like that, like T minus the transition temperature by the transition. Invented by Landau, right? This eta thing. And then it's m squared and then m to 4, right? So you divide by h, you have h by m as the x-axis and the m squared is y-axis, and then you get the slope of that's going to be this the b parameter. The b parameter is plus if it's a second order and minus if it's a first order. So if you just if you do this arrow plot of m squared versus h over m, and you can predict right away what the kind of order of transition it is. So it isn't mystical, like is it first order, is it second order? It becomes like instantly that's second order because the slope is up. The slope is down, that's first order. And then also you get from this weird plot is that the intercept of that is going to be this critical temperature thing, number one. So all you have to do is have one of these curves. You can get the intercept will give you the critical temperature. And then when that intercept goes to 0, so as you lower to get towards or you raise until you get to the critical temperature, the Curie temperature, you'll find a line that goes through 0 that lets you know you're at the critical temperature. So if you have a line that goes through 0, you're at the critical temperature. Also, just from the slope and the intercept, you can get the critical temperature. All right, so it's kind of a useful plot if you're talking about this idea of like first order, second order transition. It's the only way to say, like I showed in the DSC, when you run the DSC through glass transition, you can often get this peak that looks like a first order transition. So how do you tell, like, yes, 100%, that's a first order transition? You do this arrow plot in whatever form it would be for you. So M would become like concentration, or it could become density. So for a melting point, it would be density. It'd be like density squared versus whatever the field is, like a temperature versus density plot. I guess I haven't seen that, but basically you could do that to determine the order of that melting point. I haven't seen anyone do that, but anyway. So that's the idea here. So this is this area, even though it seems kind of not very useful, is the origin of all our understanding of phase transitions, right? So it's important to kind of look at it and see like how the equations pan out, because this is where it all, and everything else after is copying this and borrowing the idea of an order parameter, right, to talk about the materials. Anyway, so this is a kind of a nice paper to look at in that sense. It's got the arrow plot. It's got this idea of first order, second order. It definitively shows, because the slope is positive, that this is a second order transition, which it would seem like that wouldn't be a good case if you're trying to drive a refrigerator, because usually you want enthalpy to drive a refrigerator, and all he has is entropy. So he only has entropy to drive the refrigerator. And also, incidentally, so he has an entropy-driven refrigerator because it's a second order, and he's using high entropy alloys, but the high entropy alloy is not the entropy that he's transitioning here. Like he's transitioning from ferroelectric to paraelectric, so it's ordered to disordered. That gives him entropy change. But the alloy itself also is a high entropy alloy, coincidentally. So it's kind of like, it's confusing because it's entropy, but the entropy of the alloy is not what's driving, is not what he's interested in. Right, he's interested in the entropy of the transition from at the Curie point. All right, so that's said, so that's kind of confusing. What else is in here? So he wants a large delta S for this thing, and that means he has to figure out how to figure out what the delta S is in this thing. So he figures it out with equation 2 or something here. Let's see, equation 1 is how he relates. So he's plotting delta E versus TC, or he's plotting delta E and TC. So this is the whatever Heisenberg model, Stoner theory for this kind of Curie transition. The delta E should go with TC, and he demonstrates that here. Like he has delta E, TC, that's good. That means it's kind of following these models for this kind of transition. And then equation 2 is where he's getting the delta S from that he's going to use. So he's got this equation, which he says is a Maxwell equation, which we've already looked at, Maxwell relations. Right, so like, where the heck did this thing come from? That's the question, right? So I have part of the answer to that. So here, if you have, so he has, so he's got delta S equals the integral of dm dt and then dh, right? So he's got, basically this is the Maxwell for that is ds dh, and h e equals dm dt, and it would be like held like that. So there. I have to kind of run the two, but basically that's the Maxwell expression that he's starting with, that he wants. So you want this. That's the thing you want. Okay, so what can you get? So if you, by the way we did, right? So I mean, it looks like a Maxwell expression. It's like d something with something held is the other thing versus the same thing with the other thing held, right? So in that sense, it's a Maxwell. But so we got Maxwell somewhere here. So this is, I think, 39 here. So 34 maybe. Yeah, so we used the Legendre transformation to get the Maxwell, right? So you can say dA or you can say dG here. So if you do dG, it's the SDT minus the SDT VDP. So anyway, minus SDT VDP. So you see, and then you say if you use Gibbs, so you have VDP, say it's a constant pressure, you get rid of the VDP part, right? You say it's like an atmospheric pressure. Or if you use the Helmholtz free energy, it's minus SDT, which is that same term, then minus PDV, and then you say it's a constant volume, so you get rid of the PDV part. Then in either case, you're going to get minus SDT as a term. So this is a constant pressure, like a Gibbs, or it's a constant volume if you're using the Helmholtz, right? And then always you're going to add in, because we have this thing, so I was going to have like BDM, EDP, phi dq, sigma dA, so surface tension, change in area, porosity length, PDV. PDV we already have in the square, the others you just add in, right? So that's how, so you get that BDV, you just BDM and just add that in. So B is a magnetic field. So he calls it H and I call it B. And I think I've always seen the magnetic field called B, but they call it H. And the problem with calling it H is that there's already an H in your thermodynamic square, the enthalpy. So that seems, and they're doing an entropic transition. So I think calling it H in the context of thermodynamics is kind of nutty, you know, because it really confuses it. So basically whatever he calls H, you have to realize he's talking about the magnetic field, B. Okay, so I have B here. So there you have that equation, right? Then you say, okay, well, Helmholtz or Gibbs depends on temperature and magnetic field. So I have a dA or dG dt at constant M. That's minus S, that's that term. I have a dA dM at constant T. So you mix and match on the things to hold, and that's the magnetic field, right? And then, so then you can say, then I'm going to take, then I have that expression. So you can plug those derivatives into here, and then you take the second derivative with the other partner. So you have dA dt at constant M, and then you're going to do dm at constant T, like this thing, right? So that would give you dA dm is B. That would give you dB dt at constant M. So I'll write that down. We'll change that to B. dB dt at constant M equals negative. So, and then the other one would be to take the derivative dA. So the other one, so be dm. So dA dt is minus S. So minus ds dm at constant T. So that's the Maxwell that you have from his thing. From basically from taking our thing, it's not the same, right? So if I go back over here, so this is the one I have. That's from the square. From the square, I get that thing. So I'm pretty confident of that. It's from the square, it must be true, right? But this is the thing I want, and they aren't the same, right? dsdm at constant T is not dsdb at constant T in particular, right? So how do you get that? So to get that, so you say there's this expansion rule. Okay, the expansion rule. So if you have ds dm a constant t, and you want ds db a constant t, I can do that because it's the same thing held constant. So ds dB a constant t times dB dm a constant t. Okay, but I have this extra thing, right? So this side is okay. I can just swap that out with ds dB constant t, and then I have equals dB dt a constant m. And then if I have this, I can flip it over. That's the flip over rule. So it's dm dB a constant t. So I have this part, that's good. Then I have this weird thing has to equal that thing, right? So I can write that differently. So this has to equal that. So I can flip that over. If I say, so I can say like dB dt at constant m, dm dB at constant t, and then I wanted that to equal this dm dt at constant h. So I flip that over. dt dm a constant h equals, it should equal 1, but it actually equals -1 because this is a triple product rule. So I use the expansion rule, and I use the triple product rule, and I use the inverse rule, like, which are all in our rules book here. Let me go back to the rule book for differential equations for thermodynamics, which I have here someplace. This is why I wanted to, so this is on slide 22, I think. Yeah, the rule book. Here we go. So here. This is the first set of notes from the, and it's slide 22, gives the rules for like how you can live with. So this is the expansion rule, dx dy at f is dx dz at f, dz dy at f. That's the thing I used to start with. And I use this flip over rule. Like if I have 1 over that thing, it's a thing inverted. I use that a couple times, right? And then I need to use this weird thing. So this weird thing is, so I have to copy it down to remember it. dx dy at f times dy df at x times df dx at y equals -1, right? So does that, the question is, does that work? So I think this is the thing I wanted. So I have x is b, and then y is oops, sorry, yeah. So x is b, y is t, and f is m, right? So this one, that means that and that are the same. Then if I say dm, so if I say dy, that's t, so that's a t, and then dm is f, so that's dy df, a constant x is b or h is b here. Right, so that one's that one. And then the f is m, so dm and x is b. So that's dx db and t is y. So that one is that one. So I have all those through 3, but I have a -1 here. So I have this equation, except I have kind of a negative in here that's missing. Like this thing is the same as that thing, except for a negative, but the negative is like here. Like there's a negative from when I did the thermodynamic square thing. So it all works out. Yes, that is the Maxwell equation. Right. And then, so the reason you want to get that is because you want to say, so it's like, I think you should go through this yourself. And in fact, it's a homework, part of the homework. So you have to go through that yourself, because then you want to say, well, then that's where this equation comes from, is ds dh, and then equals dm dt, the constant. That's a constant t, and this is a constant h. Right. So that's the same thing. That's the same thing as this, and which he calls the Maxwell. It's the same thing as that thing that he calls a Maxwell. Right. So the Maxwell is like this thing, but you can convert to that using these. That's why you have to have all these thermodynamic relationships. You can pull them out of your hat when you're desperate. Like you're desperate. I got this thing. It doesn't look like that thing that I want. how do I get the thing I want? And you say like, oh, this could be the expansion rule, this thing, and then I end up with like three things. So it's kind of a hint, like you have three differentials, they have to equal one. That means it's a triple product, so it has to work that way. Or if that doesn't work, so usually the first thing you guess isn't gonna work, right? So I mean, so if the triple product hadn't worked, then you gotta go and like, can I do something else like the chain rule thing, or can I do one of these other things to do it? You just try everything you can try until it works. If it doesn't work, you go back to the beginning and do the first step a different way. Instead of doing the expansion rule, you do like some other thing like the chain rule to get the first one, something. So not the chain rule, you use the expansion rule instead of the chain rule for the first one, then you'd have a much more complicated expression, right? So generally, there's only one way to solve these things. Like there isn't going to be more than one. So it isn't like you could use the chain expansion rule and get the answer. Like basically, it's going to be one way where it will work out. And if it doesn't work out, maybe it isn't true, or maybe you just aren't smart enough to figure it out or whatever. But it's a game. But basically, that's why all these things exist, because you're going to get to a point where you need something. So you need something like this equation, and because you can measure. So what can you measure? You can measure the magnetization. You can measure the magnetic field you put on it. And what do you want to get? You want to get the entropy. This is a classic example. The thing you want to get, you can't get. So you can only get it from the things you want. That's when you reach for the Maxwell equation to give you what you want from what you can get. So this is a pretty good example of that. I mean, anyway, so it's that business. So that's kind of a minor step in this paper, but I think it's good to look at. He goes through a lot of things. These are the delta S versus T from his magnetization measurement. So he uses that equation to calculate this delta S from the numbers that he got, which is a magnetization and the magnetic field. Then he can get the delta S, then he can plot that versus T, and he sees this kind of transition behavior, right? So, and then from that, he can calculate the energy the thing is absorbing. They again, like these alloys are strong, so he shows they're strong. He shows a stress strain, and they got like almost 2% strain. They don't break, so they're pretty robust materials, which differentiate these from any other magnetothermal materials, because the characteristic of this gadolinium materials is brittle, and the characteristic of all the other options are that they're wicked brittle. Like they're so brittle you can't use them. So they have to take these. He lists the other options here, which is lanthanide, iron, silicon alloys, which in order to use those, they put them into epoxy polymer. So that you can't use it because it's just a powder, like it won't make a solid object. So the others all have, they don't work, So there's one group of mechanical that's doing research on this kind of material. Like, so I don't know if any of you are working with him, but so there is like activity in the department on this kind of stuff. And also these papers, like this review paper has 2,000 citations. The review paper by law or whatever, this thing. So basically this stuff is kind of an active area of research. That said, that doesn't mean that it's real. Okay. So if you go down and spool through this thing and get to the actual numbers that they're getting out of it. So they come up with, let's see, somewhere here it gives joules per kilogram of this material that they can get out of this transition. Like here, so it's about 150 joules per kilogram, right? So I ask you to kind of look up like melting water, or something like that. So, or ice. If you want to make ice, so they're getting like 150 joule per kilogram of this alloy, the high entropy He alloy, right? And then water is 33,000 joules per kilogram to go from water to ice. Say you want to make ice with your refrigerator. So you need 33,000 joules per kilogram, kilojoules per kilogram. or 33,000 joules, right? So it's like 33, anyway, it's a lot. If you try to figure it out, you can make like with a kilogram of this material, you can make a half a milligram, I think, of ice. So it's like that's not a really good refrigerator. Like basically that's nothing, right? So if you kind of look at the numbers that they're giving, and they say like, well, it's comparable to the gadolinium, you know, and it's comparable to these other things that are put into epoxy. So it's like this is pretty good because look at the mechanical properties of it. So we a huge success story. But then you actually realize like 100 joules per kilogram, a kilo of the 2.5 pounds of the stupid stuff is only giving you like this little bitty cooling, like nothing, right? So, I mean, kind of wonder like why they're doing it at that point. So, yeah, the homework. Let's see. Let's see. So, blah, 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 blah. There's a bunch of papers. So there's that review paper, and then there's the idea of the first order, second order. There's an error plot. There's a wiki page on magnetothermal refrigeration, kind of like talks about, and they give the same equation, like delta S, the MDT thing. That's the same equation we're talking about. This is there's like figures of merit for it. There's delta S and the delta T, which depends on the heat capacity, and then this. So you can kind of, I think this is pretty easy to read. I mean, relatively easy to read. So you can kind of look at that and you can see like, all right, one thing to look at is things like what company manufactures this? And the answer is no one. You know, nobody uses this. So basically, that means it probably doesn't really work. Right? If it worked, people would be like beating a path to the door and like chunking these out like crazy because refrigerator with no moving parts is kind of nice. This Banerjee paper is the origin of that Arno plot kind of is kind of detailed, and this is like the theory paper that went with it. Tells about like first order, second order, and kind of goes through that Langevin or Landau. Like here's the Landau expansion, the square of the core. That's the thing from the wiki page, basically at number 4, right? And then B changes sign plus minus for first order and second order. And I think this paper is the first place where they talked about that in 1964, I guess. But and then this is the review article on these materials. There's a second review article that I didn't mention. And there's some other papers linked for this, but this one I didn't mention. I think it's more involved in the law one. That's our paper. And then there's a question. So the Maxwell's, this asks you to do the Maxwell thing I just did. Obtain the equation using Legendre transformation, which is in the notes. And then you have to do the 2 steps that I said, like the 3 steps, right? The first one's inverse rule, insertion rule. The second one is an inverse, the expansion rule, the inverse rule. Then you have to use the triple product rule, and then you can get that expression from the Maxwell equation with the magnetic field. It's good. It shows you how you can stuff magnetic field into the thermodynamic equation just as another term, another differential term, and then you can write a Maxwell equation for it. So if you said you had, I think we had 6 Maxwell expressions, and if you include magnetic field, so you have like, I think 16 at that point. You can include electric field, then you have all of a sudden like 70. And then, so you could have magnetic and electric fields in a system and all the other thermodynamics. So basically, there's a lot of Maxwell equations you can write once you get used to just stuffing new terms into it, right? And doing the Legendre transform. So basically, whatever you can think of, like you could put surface energy and area in and get another Maxwell expression. And you could talk about what's the entropy of change when a particle absorbs onto a surface, right? You might want to know that. And then that might be driving the surface absorption of water, right? So basically, however you're thinking about things, there's a Maxwell equation for you, you can stuff into the thermodynamics. And people do that. And like when you do that, that's pretty easy to publish because no one else can do it. It's kind of thing like you're the only one that can figure that out. So it puts you in a special boat. it's a limited vote of few people, right? So they can get fortunate, not fortunate, you can fame that way. Fortune you get by robbing people, there's no simple way. Just to get a gun. Anyway, uh, so why does this indicate second order gets from, let's see, what does it say? Basis of obtain this equation using Legendre. Equation 2 from Maxwell. Why does this indicate a second order transition? Why does that indicate a second order transition? As described by law. I think you have to, I don't remember, but basically I think you have to read the law paper to figure that out. This equation, I mean, there's no enthalpy of transition. I guess is offhand, although she has H, but H is really B here. So again, like H is B, so don't think that's enthalpy. So there's no enthalpy of transition. There's no enthalpy of transition. It's a second order transition. I think that's, let me see if you can just search for, I don't remember the answer to that part. What? It's recorded.
Is it recording?
Mm-hmm. Yeah. Yeah, it's recorded. Yeah. So, let's see. Let's see. She says second order here somewhere. It says it's in this paper, so I don't remember exactly. But I think it's just because there's no enthalpy, it's just entropy. It's a lot of second order in this. Oh, it's just searching, repeated searching. So I don't see exactly where she says it. I say that she says it. Oh, here. In general, metacaloric materials are classified according to their order of phase transition, first order or second order. It has been reported equation 1 can be directly applied to materials undergoing second order phase, SOPT, a second order phase transition. While discontinuous measurement protocols are essential for first order phase transition, meaning that you're going to have an enthalpy in it. So if you're using this, there's no enthalpy of transition, so it's second order. I think that's what she means by that. And then she gives a reference without the influence of prior history of sample during each set of measurements. Reference 3 contains details of various discontinuous measurement protocols. So that's for first order transitions. So she's just talking about second order. So that's, yes, it's probably worth fishing around that. Basically, there's no enthalpy change and there's no volume change. So it's second order. It doesn't have any state parameter change like that. So, and then drive equation 2 of law from perspective of pressure. So equation 2 of law is just the Boltzmann equation. Whatever that is. I think this isn't law. Law is this one. Equation 2 is the Boltzmann equation. Delta S is R, and then X is the composition. R is a constant, X is the mole fraction of the ith element. So you're going to take, he's got 5 elements. The mole fraction of each element gives you the entropy. This assumes, so this is an ideal mixing law. Like you have these 5 things. So they're 5 marbles, like red, green, blue, magenta, something else, black, white, I guess, right? So you can throw them in a bucket and shake them up. And then that thing's going to have an entropy. So calculate the entropy of that. That's going to be the number of red, like the mole fraction of red times the number of red, but log of the mole fraction times the number. So this is just weighting each component, the prefactor, and ln of the number, ln of the mole fraction is the entropy. R ln x is a Boltzmann for the entropy, right? So that's just from Boltzmann's law, right? So and then this x prefactor is that you're going to have 5 components. So the total is going to be the fraction. So the x fraction of each one summed up, like the x is summed to 1. And then each one is modified by the entropy of that one, which is R ln x. So it ends up x ln x. So see, like this is when we have binary mixtures, this is how we'll calculate the entropy, right? So this is the standard entropy calculation. This is a penta whatever mixture. It's got 5 components. It's going to have a sum of 5 things. Right, so if you have just the components and their compositions, you can calculate what their mixing entropy would be. That's an ideal mixing entropy. You can get that from the thermodynamic square. I did that in the notes here, so you can just go back. It's in single component system 34, I think. 34, no, 30, 24. Let's see, it's one of these. Oh, it's in 39. Yes. Okay, so, yeah. So you have the square, you have G's, DG's, SDT, VDP, minus SDT plus VDP, because the sign's there. Right. So if you say it's constant temperature, you can read about the S part, and you just have DG's VDP. And then if you say it's an ideal gas, V is RT over P. Right. And then you can plug that in of dP over P, and if you integrate that, you get ln of P. So the delta G is going to be the integral of that. It's going to be P over the initial P. RT gives you the free energy of a system based on the pressure. And if you go back and say PV is in RT and T is constant, so PV by RT is N. So basically the PV RT part is between the two P's is the same. The only thing it changes is the N. Then this becomes a mole fraction, and that becomes ln of X. Basically from the pressure perspective, you can get ln of X. RT is delta G with no enthalpy, so that's basically S times T minus S times T. So S is going to be minus, it's going to be minus R ln X from this. That's like a pressure way to get it. There's three ways. There's at least three ways to get that equation. One's with kind of counting statistics. One's pressure and one's volume. So this is a pressure way. So we'll talk about that with binary mixtures, but this is kind of stuffed in here at this point, because when you talk about single component systems, this one's used because you have like a gas and it has a pressure. If it's an ideal gas, because you use that ideal gas law, it's a pressure. And if it's not an ideal gas, then you introduce this idea of a fugacity, this F. So instead of P, you swap out what the pressure would have been if it was an ideal gas. So this F fugacity becomes a number, and the ln of the fugacity is going to be equal to the chemical potential. So a lot of times in certain engineering disciplines, people will just talk about the fugacity, and they really mean the chemical potential, which is dG/dN, right? So basically, from this pressure thing, you end up with a way of talking about the thermodynamic state of a single component system based on its fugacity. So you could calculate the chemical potential, divide by RT, and take the exponential of that and get the fugacity. It's kind of like an exponential of the chemical potential is the fugacity, right? So that, or the log of the fugacity is the chemical potential. Fugacity is going to have units of pressure. So people like to have units of pressure, like megapascal or Pascal. So they have some idea what that is. They don't like, I guess, joules or whatever. So basically, if you like pressure, fugacity is a better way to talk about chemical potential. So you can plot like fugacity as a function of whatever temperature or something, and then plot out the phase diagram, plot up the free energy plot for a single component system. That's why that's in the notes here. But so the question and the homework is, let's see, homework 3, derive equation 2 from for pressure. Oh, it asks you to do it for volume 2. Statistical mechanics is just Boltzmann's law. Like you have the number of state ln of the number of states gives you the entropy. Right? That's just the Boltzmann's law. The volume one is the same thing. It's similar to that I just did, or what I have in the notes here. Is it right after that in here? I don't know. Nope. The volume one, I don't have right now. It's let's see. gonna be what? Let's see. The volume, you need the dV. I don't remember the volume one right now. If you can't get the volume one, that's okay, because I don't remember how to do it right now. They ask you to do the pressure. The pressure one's there. The volume one, I don't remember how to do it right now. And then statistical mechanics is just like the Boltzmann's law, which is like one of the number of states gives you the entropy. That one isn't, you don't really need to derive that. That's kind of stated by Boltzmann, right? So explain how the arrow plots in figure 4b and d to determine the Curie temperature. That's kind of here. So you get, with T minus TC. So if you have the intercept of this, you get that number, and then that's got whatever temperature you ran it at. So whatever the intercept is A times that thing, and from that thing you get TC if you know what temperature is. So the intercept of this gives you that number. So, and then that's on the wiki page. How does this plot relate to Landau theory for second order phase transitions? That's like, this equation is the Landau theory equation, like the HM m squared m4. It's the same thing as what I did in inside here for the Landau theory. It's basically, this whole thing was written up from the Landau theory, which is like somewhere here. Second order transition, it's got like the square on the fourth term. You can also have like an extra term here, like A lambda, B lambda squared. And so this is like a background, a bias, I guess, term. Like in this derivation of it, they don't have the bias. So they, like, this is F minus F0, for instance. So basically this just has a square and fourth term, but anyway, that's the same as like this equation is the Landau equation. And then even in that derivation, this T minus TC becomes the argument for A. I think that's what A is here. A is T minus TC. So it's the same. It's kind of the same thing. It's basically exactly the same. It has to be, because this equation is Landau's equation, just written in a different way. Like, so Landau theory, second order, where's TC from these plots? So you get it from the intercept, and then or the slope and the intercept both can give it to you, or you can get it like if you reach TC, then the thing intercepts is 0. So if you find that, if you happen to get to the critical temperature, then you have a 0 intercept for it. Right. So, and then approximately how many grams of ice could be formed from water? So you have to look up what the enthalpy of fusion is for water. You find out it's about like a milligram or something, like almost nothing. And that means that commenting on usefulness is not useful, in my opinion. So you could maybe come up with another conclusion. And this thing is about, so it's a mixture. So the entropy, when he says high entropy alloy, he means that he has this mixture of 5 components, and it's in a perfect PCC crystal, but the components can be located at any of the possible sites. So because of that, it's high entropy, because there's a number of different states. So given a 50-50, given a mixture of all these components, like 10% each, whatever it is, and then basically they can be located anywhere. And if you include all the possible states that it could be located and take the log of that to get the entropy, you get a big number. So it's a high entropy. But that isn't the entropy of the transition, which he's looking for to drive the refrigerator. Right? So it's a little kind of an odd twist there. So then calculates the entropy change in the second order transition. So it's like when she calculates, so the entropy of mixing, so when Law calculates the entropy here, that's the mixing entropy. That doesn't have to do with the entropy driving this cooling process. So the high entropy alloy, this is telling you how high the entropy of the alloy is just by the composition, because they're randomly arranged like an ideal gas, totally randomly mixed. but that isn't the thing that's driving the transition of the thing, right? So that doesn't change between the Curie or the between the ferroelectric or paraelectric states. It's the same high entropy alloy before and after. What is the relationship between entropy change shown in figure 5 and the high entropy on main? There's no relationship. They aren't related. And then what advantage do high entropy alloys have over MT? So the other MT materials, gallium, seems to be the only thing that's really used. And that thing's brittle and it oxidizes. So it's not stable. So these things are stable and they have a good mechanical strength, which they show in the last slide. They show that in that last plot, that you get this mechanical behavior. If you read his paper, like the beginning part of this thing tells you why. The first paragraph, he has like 3 paragraphs where he says why these are better than other ones. So some of these, like 1 to 10, there's 2 Nature papers in there, and the 1 to 5 isn't 1 Nature paper. It's basically there's a lot of like high impact journal articles in this field, you know, but it doesn't mean that it's important, you know. So it's kind of like you have to. There's a lot of citations for this stuff too, so you have to kind of like look at the bottom line and say, well, what exactly? If you hear someone give a talk on this and they say, I get 150 joule per kilogram, then you have to realize that that's like nothing. Like there's no heat in that thing at all. It's like, why are you even doing this? So that should be your first question when someone gives a talk on this. Like at what state? You know, it's like someone talks about fusion reactor and, oh, we finally achieved generation of more electricity, more energy than what we put in after 50 years of basically $100 billion a year of research. You know, it's like, well, that was really not a good deal. You know, like we could have solved global warming with that money easily, you know, instead of trying to chase after fusion energy. So it's important to kind of put people on the spot and like say, like, why are you doing this? And is this really worth what we spend money after? So, but on the other hand, maybe they'll make a great refrigerator sometime. It's like superconductors. People looked and looked and looked, and then finally found some that are like room temperature. So it's like that's a pretty big deal. They're not processable, so you can't really use them. But basically, it is a pretty big deal. Like it could save a lot of energy if you had no resistance. So anyway, I think that's about. Any questions or anything on this? Should be recorded. I did the same homework last year, so if it's not recorded, there's a recording of it from last year too. So I just kind of ran out of time this week. I'm not sure why. There's no real excuse, just somehow I ran out of time. So I used the same one, but actually it's a pretty good one because it's got this, it makes you do the differential math stuff and kind of figure out why you're doing it because you need it for this to do this particular application. And then it introduces you to this kind of field, this kind of high entropy alloy field. So if you hear a talk on that, you might be more interested in hearing it. And this refrigeration thing, magnetocaloric refrigeration topic, which is a kind of a hot topic. So, so it's a good paper to look at. It's kind of complicated. It also gives you some things you won't know about, like this density functional theory simulations of atomic orbital stuff and a couple other things that we'll talk about later on. So it's feeding you things that you won't know about, but you can kind of see the words, and when you hear them again, you'll be like, I heard that word somewhere. Yeah. So it's helpful to have that introduced that way. Because if you hear it enough, then you'll look it up. You look at the wiki page or something. Density functional theory, you still won't understand it. Like even if you look it up, so it's going to be like, that's a pretty deep thing. Like you need quantum mechanics and things to figure out roughly what they're talking about. And even then, I think if you're going to do it, you have to have a ton of money. Like the software is in the hundreds of thousands a year to run it. So it's kind of like your average Joe is not going to do this. So you have to have it like a group that's doing that kind of work. And then, so anyway, it's a kind of a funny little, but everyone that's doing this kind of atomic level metal things is going to be using density functional to predict the properties. So it's good to know the word. And maybe you'll have someone that can afford the software to do it. There's no shareware. Like I like things where there's a shareware you can download on the internet or you can steal it and use it. Those are good things. And things that are like so packaged. One thing you'll never know if it's true, it's a black box. Like you're using this thing, you have no idea if it's true or not. You're just trusting that someone kind of figured it out, which is not a good place to be because you don't know where it's going to fail on you and things. Anyway, so no questions on this thing. I didn't really finish the chapter, so I want to do it so I get through the whole thing, but basically I think I have 10 minutes. So why don't I just try to see if I can finish this section, whatever's left here. So we did the Landau things. Let me just see what's missing. Hopefully you'll get this stuff by kind of fishing through it and you get some feeling for it. I went through the, so I went, last time I kind of went through the van der Waals equation of states, this idea, so you have PVs in RT, PV RT over V, it's ideal gas, and the V is specific volume, so it's got the N in it. Right, so that's like dense one, it would be P is rho RT, like density. So mass per volume. Right? So that's ideal gas. That means the particles can pass through each other. And then if you want to say, and the first thing you would say, like, well, they can't pass through each other, so there's excluded volumes. You make this B thing. If you include that, the pressure has to go up. So if you reduce the denominator, then the number goes higher. Right? So you're reducing the denominator, the pressure goes up. That makes sense. And then you want to have phase transitions. So that'll only keep you in a liquid state. That won't give you like a solid state, or it only just keeps you in the gas state while you have a condensed phase. So to have a condensed phase, you have to have an attractive potential. And the simplest one's a binary potential. So two things interacting. So it's that number that's the potential of interaction times the square of the density, V1 over V squared. Right, so you end up with this equation's the fundamental cubic equation of state, or called the van der Waals equation. And that still is the fundamental thing that you would use, even though it's from the 1800s. Still like the best thing to use because it's simple. You have a really good grip on what B is and what A is. If you start making it more complicated, so think for petrochemicals like the ethane, like carbon chain materials, right? Alkanes. Then basically this Ping-Robeson state was invented, right? So it's the same, if you look at it, it's the same as this. It's got a B, so it's got an excluded volume. It's got rho is 1 over V. So it's kind of, the first term's almost like this. Then it has an A term, it's just that they've mixed the two up. So they have like B and A coupled together. So this turns out you can predict the properties like everything with this. So it's pretty useful. Especially single component systems, right? So the PVT behavior, ammonia, whatever you want, works with this pretty much. And all the things that this equation depends on are you can reduce this down to the critical parameters, so you can have the critical temperature, pressure, volume, and you can calculate what the A and B are in this thing. So you can do this whole thing with just the critical parameters, because you have these expressions like at the critical point, dP/dV is 0, the second derivative is 0, and the third derivative is 0. So from that, you can calculate like what A and B are. Like you can take the van der Waals equation, then do these derivatives to it, and then solve for A and B, because these two derivatives would give you two equations, and there's two unknowns. And if you solve those, if that's 0 at the critical point, then you can solve and get the expressions like a universal law based on the critical point of any material. So you can predict the phase behavior of any material based on a measurable number, which is a critical temperature pressure. So, and then the same thing you can do with the Peng-Robinson. You can do the derivatives, get those. There's only two parameters in it, so you can do that with this also. So basically, if you're using this in a software, the software will ask you to input the critical temperature, critical pressure, and it'll give you the phase behavior of water, for instance. It's a popular one. So you can get the behavior, the total behavior of water for every possible condition. If you want to know the pressure inside a boiler or something, it'll give you that. And then these things, if you multiply by v squared and by v, then you're gonna end up with v cubed. So that's why it's a cubic equation of state. So if you write that out, you're gonna get like so if you write it in terms of the z, what's that thing called? The z. So that would be the what's z called? I have it in here somewhere. It's definitely in here. Z called, I don't remember. Anyway, the z, you write it in a series of z. Z would be 1 for an ideal gas, and then the partition, no, not the partition, the compressibility factor. Yeah, right here. It was in there. So anyway, right in terms of the compressibility factor, and then you can write the cubic equation in terms of compressibility factor. So basically it's volume cubed, because you have volume squared times volume gives you volume cubed. So you have a cube squared first order and then a constant. So you have basically like that, and these A, B, C numbers are defined somewhere here. Maybe not. Anyway, the ABCs are just defined in terms of DNA, right? So it's basically everything's DNA. So all these AB numbers are DNA equations, right? And then you can solve this equation, and what you're going to find out is you'll get multiple roots for it. So if you plot the free energy, so this is the kind of the equation. So if you plot versus the compressibility factor, so PV over RT, then this is the free energy by the cubic equation of state. So basically, the free energy is going to look like this. It's going to have multiple roots. If you're at some value here, so you got like 1, 2, 3 roots. For a cubic equation, you have 3 possible answers. So that would be in a two-phase state. So you have one free energies, the low P1 is going to be the vapor state, and the high P1 is going to be the vapor state. So liquid and vapor. And there's this weird thing in between that's doesn't exist. So there's another root that doesn't. So there's 3 answers to this equation at a given set of conditions in the two-phase region. If you get to the one-phase region, then there's like one answer, right? So when it's a liquid, it's that answer. When it's a vapor, it's that answer. And at the critical point, the equation like has a range of answers. Like it isn't just one answer, right? So basically, the cubic equation of state will always have, when you solve it, the expression is going to always have multiple roots to it. Right? So that's why they call it a cubic equation of state. And the simplest one is the van der Waals. And then you can get more and more complicated ones depending on what you want to put into this. You can add other parameters other than A and B. Like you can put the acentric factor, you can put like a polarity factor. So people just keep piling on other factors into these equations of states that make it so complicated you have no idea what they're talking about. But they're written kind of for one particular material. You know, but the most general is van der Waals. And kind of the most useful is a Peng-Robinson. And then there's others that you can use if you're kind of desperate, you know, for different things. But that's kind of about it. That's cubic. This is really for alloys, so mixtures of things. So yeah, that's kind of it for the single component stuff. It's probably enough. So if you do this paper, I think that'll be good. You know, if you have questions, email me. You know, and I can help you. You can try to work in the group. Oh, there'll be a recording of it, so you can look at that if you want. Remove last year's recording. Should be, hopefully it's good enough to do that. So, all right, that's about it then. There's no questions or anything. No. I'm teaching another class, is plastics recycling class. There's a guy coming in to talk today at 3:30 if anyone's interested. It's like a guy from the polyolefin industry talking about recycling plastics. At 3:30 and 3200 Rec Center, but you can come if you want. But you know, it should be interesting, I think. But